Welcome. A little bit more about group theory today. It's Halloween. Welcome to this Halloween lecture. During the last week I was learning a little bit more about the problem of the extension problem for groups. And the reason was that we have looked at groups which are not natural. A group is natural if it is obtained from a metric space. And what I have looked at examples and saw that the Z4, the cyclic group with 4 elements, is not natural. Also, that was actually the starting point. Also, the integers were not natural, and also the Q8, which is the quaternion group, a finite group of order 8, is not natural. And when I was looking a little bit more about this problem of group extension, because one of the big questions is what happens when you take a semi-direct product of two natural groups. Is it natural? So that's the question which I cannot still answer. I think the answer is yes, and it's probably not so difficult to prove, but this is the big question. So why not look at many examples of groups? And it's actually a very interesting topic, this group extension problem. And let's just start at the very beginning with a big program. The program of understanding groups is to decompose it into simple groups. They're called simple groups, and the theorem which allows you to do that is the Jordan-Hölder theorem. And so you build this composition theory series. You take the largest, if you take a group, you take the largest normal subgroup, or one largest normal subgroup and maximal normal subgroup, and then you build this composition factor. And you do that then with successively with this normal subgroup again. You find the maximal normal subgroup, etc. And so what you get is this composition series. This is not unique, but the factors, these quotients, are up to permutations unique. So that's a generalization of the fundamental theorem of arithmetic, which decomposes numbers into prime numbers. But there is a big problem. Why we know these atoms, this is especially in the finite, no, actually only in the finite case of finite groups. One has a list of all the finite simple groups. How do we actually what is the structure of the set of all groups? I mean, especially important is which groups can you no more split into smaller groups. And so there are classes of groups which examples of groups which are not simple, so they have normal subgroups, but they cannot be written as a semi-direct product. And that's very interesting, and for me this is very interesting because it just happens to be very similar also with this problem of which groups are natural. So especially these three examples here of groups which I had considered. So this program, even for simple groups, this is considered to be difficult. One doesn't know which groups can split. There is a theorem which, for example, says it's a Schur-Zassenhaus theorem, which says that if the index, so the G over n, the index of the normal group and the order of the normal group are co-prime, then yes, you can split it. But in general, I think this is completely unknown. So let's look. That's the first thing. That's kind of the big picture behind it. This structure of groups, and let's look at the problem of splitting groups. And so if there is a normal subgroup, so that you can write the group as a semi-direct product of the normal group with and that has then to be the quotient n. This h is then just g over n. That's a quotient group. If you can write it as a semi-direct product, then you say the group splits. I like to think about this as a fiber bundle. It's not original, but you should think about the h as the base and the n is the fiber. So that's justified by examples. And so what you have is the h then acts on the on the fiber. So when you look at the semi-direct product, then you have the base multiplies. So I'm writing the base to the left, like what you do in mathematical physics. You know, the base is the first thing, and then this is kind of like the gauge group here. So xg multiplied with yh. So you multiply in the base group h, and then on the fibers you have a h multiplied with an action of x on z. So we call this g to the x. I learned this in some course of Borchert, who has a group theory course on YouTube. And so maybe it would be better than to flip things around and have the h before. But usually kind of what you see in the literature is that the n is before the h. By the way, about the notation, so this is kind of this cross. You can remember this. This is a multiplication sign, and then you have also a triangle. The triangle is from the normal subgroup, so you can remember it. The n is a normal subgroup because you use this triangle for the normal subgroup. So that's how you can remember this symbol. There are other notations like Barry Simon uses in his book on group representations. Just the S, maybe because of Simon. Semi-direct product. So what we have is the semi-direct product is something very, very natural, and we just see that in examples. And there's also this notation. I like this notation of Borchert's. So if that is possible, if you can write the group as a semi-direct product of this base H with the normal group, then it's called, we say the group splits. And so it's a split extension. And so there's also kind of some notation here. So the n this is a short exact sequence, and that's the n, that's the normal group. So the kernel of this map here is trivial, which means that n is embedded in G. So that's what happens also in a fiber bundle. So the n is embedded, and then what we have, this is the projection from G onto the H, which is G over n. So that's the picture. So F is this projection from G onto H, and then this is the kernel of F. That's always every normal group is this kernel of projection map onto the quotient, and then the image is that. So that's the base. About 11 years ago, Terry Tao has in his blog kind of illustrated this a little bit, and kind of says, think about G as the picture, and then you apply a filter like n, and then you get a pixelized kind of a rougher picture. But so that's the H, that's the base that has much less information, and that's the thing. So there are two fundamental things, which are embedding something or then having it as a cover. So there are two dual operations, and you see that here. So it's kind of embedding and the cover. So if you think about covers, you think about fiber bundles. So that's part 3, some examples of such group extensions. So what I started with here, and kind of how this whole thing started, is with the observation that Z is not natural. So Z has normal subgroups. For example, 5C is a normal subgroup, but you cannot write it as 5C cross C5. That's just, not possible. It's not a simple group, but it cannot be split. So it's a non-simple group which cannot be split. This is exactly this example here. But then if you make this dihedral group, you should think about this as the space has 2 points, and each fiber is C. And then you have this kind of half, I consider them as half integers, and these half integers are more natural. It's also, in some sense, it's very natural that you don't have to introduce any number system. And also historically came before the number system were introduced. The Ishango bone, for example, has just marks. So the mark is A, the gap is B, A, B, A, B. So you don't introduce numbers yet. It needed tens of thousands of years to get them to the number systems, like the Sumerians introduced the place value system. So that's much more sophisticated way to write. This is a much more primitive way to think about numbers. God has created the half integers. So we have to modify this Chronicle thing. God had created the half integers, and all the rest has been produced by mankind, humankind. So this is this is the first example. And then of course also the dihedral groups, the Zn are not natural. So here we have to kind of break the symmetry. If you break the symmetry that this is longer than that, we get the matrix space which has only one group structure, the dihedral group. And that's, for example, that's these three here. You can generalize this. This Z2 appears often. You see that often in cases, even in the Rubik cube. When you look at the Rubik cube, so there is this Z2 semi-direct product with Z2 which appears. We will come to this. But you can also take other groups like cyclic groups. And a very nice example is this Frobenius group. This is so when you look at groups of order 21, there are only two. There's Z21, which is the, direct product of Z7 with Z3 by the fundamental theorem of abelian groups. But then there is another group, and this is Z7, and you take the semi-direct product with Z3. So it is a very interesting thing. It's more generally, you can actually define Frobenius groups more generally. This is the J. I think we'll come to this. But what it is actually, kind of, you think about it as the Euclidean group on Fano planes, on the Fano plane, which is the smallest projective plane. So there are translations and there are scalings, and we will see that the kind of translations, this has a normal subgroup of Euclidean group of the Poincaré group. So you have all the time this kind of this structure of the semi-direct product groups which are important in physics. And so that's an example of a Frobenius group. Also this Dn are Frobenius groups. So if you look at I like this example of the Euclidean translations. That's kind of something you learn very early when you are doing geometry. So there are translations in the plane, but there are also rotations. Now this is already a non-commutative group, right? If you translate and then rotate, that's the same. That's different thing than if you rotate and translate. So that's you can think about this as the semi-direct product of, in this case, if you look at orientation preserving things, then it's SO2, which is just a circle, all the rotations. So that's the base, and that's the fiber. The fiber is R2. So this is an example of a vector bundle. It's very nice, and if you look at the multiplication, you can do the multiplication. You see kind of the rotations are just rotating. But if you do this, the translations have to be conjugated here. So this is a vector bundle on the circle, and that works also in arbitrary dimensions. You take Rn semi-direct with SON or with ON if you have also the reflections. And that's also happens when you have different signatures, different quadratic forms, which are invariant, like the Poincaré group is very important in physics. We have the translations, and then we have the Lorentz group. So the Lorentz group is the base, and then the fibers are these translations. And so you have so essentially R4 here, and that splits. So that's related to this is also just an algebraic picture. If you look at the affine transformation, like an affine transformation is a linear transformation plus a translation. So this is a semi-direct product of Rn. The translations are the normal group, and then you have the base, which is here the general linear group. So this is called the affine group. And you can write this down just with matrices, right? This is when you do that, this is a matrix which is invertible. So it's a multiplicative group of matrices here, and the translation is this is just it's a normal subgroup. And here's an example also which you can do in general, which somehow the most general extension you can do is you have the entire automorphism group, because all of these things what you do in the fiber is are automorphisms. So that's kind of every extension somehow is in this. This is called a holomorph, where you have where you extend an arbitrary group. This is a very beautiful example, and I actually looked at this because I wondered whether it's natural, and I know now it's natural. So A4, that's the alternating group. It's a very, very interesting group because it's the only alternating group which is not simple. So it splits as it has a normal subgroup, which is, so A4 has A4 has 12 elements, so 12 divided by 2, this is 6. So this should be these 3. I was wrong. You can build this truncated tetrahedron. So you take a tetrahedron, you take away the corners, and then you get or you can get a graph here. And so the only symmetries, the symmetries is actually, so this has 12 elements, and you have just the alternating group is the only group which works here. That's one of these principles which we have seen last time. If the automorphism group is the number of vertices of a graph. So this is very nice group. It's the tetrahedral group. Then there is S4, which is a cover of A4, which is the octahedral hexahedral group, which also is natural. So what you can do is you just take the octahedron instead of, I don't have an octahedron, or you take the cube and you take away the corners. So you can do that, and that has then 24. This is has 24 elements. This is a symmetry group of the cube, and or octahedron. So that's a very natural. These are very natural. I mean, you see that in this sacred geometry picture of the Metatron. So it has all this kind of tetrahedron and octahedron. So all these Platonic solids are very classical, and you see them also in group theory here, kind of coming in naturally. And then there is S5, which is A5 semi-direct with Z2, and this is now A5 can no more be split. That's a simple group, like an atom. It's also natural, and we can also build here just as we take the icosahedron or dodecahedron, and you make it. So S5 has 120 elements and 60 elements in thing. So if you take 20, it has 20 corners times these 360. So you just cut off every corner here, and then you have you have a graph with 60 elements, and the only symmetries are this. You make this dihedral construction to get also S5. So this is a very a general example of kind of dynamical system theory. You think about G as a dynamical system as time acting on some space. Every non-zero, or not the identity, if you have not the identity here, has either 1 or 0 fixed points. And then you can take the ones which have no fixed point and add the identity. It's kind of the identity. This is the identity here. If you take that as your, the theorem is that this is a normal group, splits, that's called the Frobenius complement. And this example which we have seen here is kind of just of this type. So that's, I think, also important in number theory, or this Frobenius story. Back to C4, is actually a funny group. It's also called pin -1. So there's this joke of Sayre, which says that pin is over O and what spin is over SON. I think this is reported by in an article of Diabot and Shapiro in the 60s. And so this is but it's kind of interesting that we have here already for a group of order 4, a cyclic group of order 4, which is very it's not simple, right? It's not a simple group because it has normal subgroups, Z2, but it doesn't split. So the Klein 4 group, that's the Z2 times C2, which is also the dihedral group with 4 elements. This is also this is natural, but this one is not natural. And the other one which I just looked at, which I thought it's not natural, is Q8, which also does not split. So there is kind of some kind of suspicion that there is a relation between these two concepts. Either if something does not split, it has a chance to be non-natural. So most groups are probably natural because most groups split, and so that's the picture. But I don't know how to prove that. Now, the last thing, or one of the last things, is that's kind of one of my favorite. That's kind of the start how I got into group theory. When as a high school student looked at the Rubik cube, and when you look at the Rubik cube and you play with it, you don't know any group theory. It's very clear that they are just, it's permutations of the, you have permutations of these cubes. But there is an additional thing which can happen, is that some corners can turn. You cannot turn one corner by 120 degrees. That doesn't work, and that's a kind of a quark. So, but you can have one and then turn the other in the other one. That's a meson, or you can have three turn. You have this structure which you see in the standard model for particle physics. You see this thing, but it's funny. Somebody wrote an article about this that you actually see these quark structures also here. So that's the reason when you take, this is the 2 times 2, 2 times 2 times 2 Rubik cube, which is just the corner group of the regular Rubik cube. So you ignore what happens with the edges. So you have only the corners. And what we have is then, so we have the permutation group of all the corners. That's the base. That's the base, and then there is the fibers. It's the C3 to the 7, not C3 to the 8, because all of them have been fixed except one. Also, the last one is fixed. So I think this is natural, and just because I believe that every semi-direct product is natural, I think S8 is natural, which I have not yet proven, but I think it's true just by looking at some Cayley graph, metric space given by Cayley graph. It should be, I think it should be working. For example, you take two generators, one transposition and one cyclic. This generates the whole S8, and then you build the Cayley graph and you take this as a metric space. So that should work. And then one should prove similarly then the product of two groups, direct product of two groups. Also the semi-direct product of two groups is natural. And if that's the case, then this is natural. So this group would be natural. And also this group, that's the larger, the Rubik. Rubik is a little bit more complicated because there are now also edges. No, that's the fiber. The fiber is kind of, that's the fibers are like the gauge group. These are the turning of the cubes and the edges. So this is kind of like a gauge group. This is the normal group, and then you have the base is the permutation group of the, or the alternating group of the corners times the alternating group of the edges, and then they are also linked together. And so you have here also already a semi-direct product, then you have again a semi-direct product. So that's the structure of the Rubik cube. I mean, if you know this structure, and if you know that the direct products, if you know that semi-direct products are natural, and you know that A8 and A12 are natural, then Z3 is natural and Z2 is natural. Then you have that also the Rubik cube is natural. I think that's true, but I'm not sure that. But I think I will wrap up this thing without actually trying to prove this. And then we have the last example, which I should mention, is just an orthogonal group. It's a semi-direct product of the special orthogonal group. That's it for today.